Okay, good morning everybody. It's a great pleasure to be here and thank you a lot for this nice prize. So, my name is Xavier Crispin and I'm working at Linköpings University and my research topic is about the conversion of heat into electricity. And why it is important is because there is heat everywhere. If you use fossil energy in an engine to produce motion or electricity, 60% of that energy is lost in heat. Or if you use the sun to try to get electricity with the photovoltaics, you have about 70% that will be lost in heat, basically. Another interesting heat source is the body. So it could be nice to transform heat into electricity directly. And this is possible thanks to thermoelectric generators. And these are actually semiconducting electronic devices that looks a little bit like this, and you put that between a hot source and a cold side, and there will be a heat flow, and the heat flow will carry electrical current. So they have been developed first to power satellite, actually, and nowadays they are scrutinized to try to get some electricity in cars on the exhaust pipe and the radiator. They have been also miniaturized and integrated in a watch, so that this watch is powered by the heat of the body. And nowadays there are kind of cool products on the internet where people are trying to develop basically thermoelectric for charging mobile phones. But we are not yet there, but there is a potential for that. So why these kind of thermoelectric generators are not on the market really is because the price of the material, the cost of the material is quite high, because the material are composed of atomic elements that are of low abundances. So what are thermoelectric materials? How it works is that if you have these materials and you put that between a hot side and a cold side, it actually generates a voltage. And since the material is an electrical conductor, it actually also produces an electrical current and electrical power. So what kind of properties we would like to have for thermoelectric materials? It's gathered like this. We want to have a high electrical conductivity, a low thermal conductivity, and a high Seebeck coefficient. So those properties are gathered together in what is called the figure of merit, ZT, which actually tells about the efficiency of the conversion process. So in order for you to grasp what are thermoelectric material, I describe here two axes, the electrical conductivity and the thermal conductivity. And you see that we can split like this classes of materials. When both conductivities are high, we have metals. When both conductivities are low, we have plastic, for instance. Thermoelectric materials are not really designed by nature, but we have to design that ourselves. There are very special class of materials here where basically it's a thermal insulator like a plastic we are looking for, and an electrical conductor like a metal. So since I've worked on kind of conducting polymers for years, then when I saw that opportunity, I thought let's try to investigate if it's possible to make a thermoelectric material with conducting polymers. And this is an example of a conducting polymers. You see it's based on carbon atoms that we don't see here, sulfur and oxygen atoms. So they are all very abundant on Earth. So if we can make a thermoelectric material with that, it would be a quite interesting finding. Moreover, one of the interesting things with polymers is that they can be solution process, which means that eventually you can create a thermoelectric ink, and use a big printing press to print thermoelectric generators on plastic foil or paper. And that would be also another key advantage in terms of manufacturing cost. So both the low cost from the material and the low cost from the manufacturing would be a key point. So this is what we have done, basically. We have studied and optimized the thermoelectric properties of these kind of conducting polymers. We have found ways to improve that by improving the molecular order and also tuning the doping level or oxidation level. So you can see that as a semiconductor. So when, for instance, here we will investigate the three properties: electrical conductivity, Seebeck coefficient, and thermal conductivity. So when you increase the doping level, the electrical conductivity increases. In the same time, the thermal conductivity also increases because part of the thermal conductivity is due to the charge carriers that are carrying heat. However, the value of thermal conductivity is still very low because it's a plastic, it's a thermal insulator. But we have also, when we increase the oxidation level, the decrease of the Seebeck coefficient. So those cancel each other. And somewhere in the middle, there is an optimum here. And this is what we found here. The optimum for ZT, which describes the conversion efficiency, is about 22% there. And there, the material, the conducting polymer, optimized, start to be a thermoelectric material. So here is a graph where I report the value of ZT at room temperature versus the years, and compare the inorganic one, which is the state of the art is bismuth telluride. You see telluride are atoms that are not very abundant. It's quite an efficient material. And here, after our findings, there have been other research steps that have been achieved by the different research groups in the world, showing an increase of the ZT value, basically. And so it's improving, and if we want to have an idea about what means thermoelectric generators, for a ZT of 1, so for the state-of-the-art inorganic material, the conversion efficiency is about 5% when you have a temperature gradient of 100 degrees on the material. So if you reach a ZT of 0.3, this is what we have achieved, basically, then we can go to 2% for the same temperature gradient. So it's not that great, but it's improving, and we will see where it ends. I don't know yet if there will be any viable technology based on that material, but it's certainly worth to try and search a little bit more. So I would like to thank the Laboratory of Organic Electronics, because certainly this prize is an award for all the groups, and we have been several people working actively on that. And it's not possible without fundings, and there is Advanced Functional Materials, governmental grant from the Linköpings University, SSF, the ERC grant, starting grant, the Energimyndigheten, the Knut and Alice Wallenberg Stiftelser, and my Lord for spiritual support. And I thank you for your attention.